So let's take a simple, easy example. This will be a thought experiment. Imagine I have the ability to put a voltage on a system that looks like so. So this might be at 0 volts, and this would be at 0 volts, but this would be at some voltage, and this would be at some voltage. And now I have a particle that's trapped. Let's say it's a negatively charged particle to kind of match with the, that's the way I've set my voltage sources up here. If I were to graph the potential energy of this particle, it might look like this. So this might be location A, and this is B, this is B, this is A. The particle would have to climb up to some voltage, V0, in order to reach either of these points A, but it lives in a state of 0 potential out here in the middle. So if the energy of this particle happens to be rather small, then it will be trapped. It will be bound inside of this system. And be confined to live within this range right here. We're going to imagine a limit where this potential goes to infinitely large, and that B goes to A, so that the potential energy is 0 in between 0 and L, but goes to infinitely large if you're outside of 0 and L. Inside the box, the energy of the particle is just kinetic. In other words, it's just p squared over 2m, since E of x is equal to 0. As a result, the time-independent Schrödinger equation is rather simple, because this term goes to 0. And we have a differential equation that looks like this. I'm going to rewrite that as minus k squared psi, where k, this is defined to be 2me square root over h bar. Now the candidate solutions will look something like traveling waves, e to the I kx. but we have boundary conditions now. We would like the wave function to go to 0 as x either goes to 0 or x goes to L, and that's because the potential has gone to infinity up here at 0 and L. And if this wave function has something to do with probability, we know that the wave function should probably go to 0 at these locations. So the general solution will look something like a superposition of such plane waves. Some moving to the left and some moving to the right. Or another way to think of it is k could have either plus or negative sign, because all we needed to do here was to have k squared equal this thing. So the square root of k can either be positive or negative. And all we know is that C1 and C2 are constants. Now, psi of 0 equals 0 imposes a constraint, and that is that C2 has to equal minus C1, because psi of 0 gives me an e to the I k0, that's 1, and an e to the minus I k0, that's 1. And I have psi of 0 just equals C2 plus C1. That only equals 0 if these two things are equal and opposite. As a result, psi of x looks something like this. Now you may recognize that a difference in two exponentials like that, e to the I kx and e to the minus I kx, will look something like this. So e to the I theta minus e to the minus I theta is 2i times sine of theta. I'm going to just rewrite that. Is that wave function is some amplitude times sine of kx. A is a constant. We don't know what it is yet. We also have to satisfy the boundary condition that psi of L has to equal 0, which means that sine of KL is 0, and that happens as long as KL is a multiple of pi, any multiple in fact, where K is n pi over L. The energies are then restricted. So notice that this means it's quantized. Values of K, not any value of K will do. The energies are kinetic, and they're required to be h bar squared k squared over 2m, and that's just p squared over 2m. We can insert our newfound value for k. And there's a lot of pi's in here, so there's a pi squared there, and there's a 1 over 2 pi squared there. So I'm going to write this as h squared, not h bar. That's h, not h bar. This is the length of the box, and this is an integer m. And psi of x and t is equal to some constant It looks like so. So it's a constant times sine n pi x over L, e to the minus I omega t. Notice I've rewritten omega as the energy divided by h bar. And psi has to be 0 outside of that range. These wave functions look rather familiar.